For the second talk this morning, we have Asvin Gothandaraman talking about matrix points on varieties.
Yeah, thank you for the invitation to speak. It's a wonderful workshop. So keeping with the theme of the conference, I think this is a little bit outside of what other people have been talking about. But the connection I want to make is that this is the way of thinking about what non-commutative cycles might mean on a variety. Right? So I'm going to try and make the case that this is some sort of interesting object to study, and it has connections to what you might think of as classical cycles on a variety. Okay, so let me first start off by motivating what we're going to do. So let me just start off by talking about cycles, and let me focus on zero cycles. So cycle on a variety. And the classical way you might study this is that if you have a variety X, you might consider Sym_n of X. Okay, so this is the quotient of X over n by the symmetric group. And what this object corresponds to is that if you have a point on Sym_n of X, that's the same as giving an n cycle on X. Because if I pick a k point on Sym_n of X, then I'm going to pick n points on X power n up to this permutation by Sn. Right? So you can think of this as some sort of geometric object parameterizing an n cycle on X. Right? So what I want to try and make the case for in this example, in this talk, is one way of thinking about this is that if you have a k point, so k point of Sym_n, you can think of as being the same as giving an algebra L over K. So this is a finite. Algebra with an Sn action and a map Sn equivalent map from spec n to X power n. So with here you can take for L either a direct sum of n copies of K, or maybe a Galois field extension. So you can think of Sym_n of X as parameterizing extensions L over K up to along with the map to X power n. But one thing you can ask is, okay, so this is sort of a commutative extension of K. But there are also non-commutative algebra extensions of K, which maybe you should think of as in living in the same world as K. So you can try and study what happens if I allow for extensions, not just with commutative algebras, but non-commutative algebra. So here's a question. If we allow L equal to Mn of K, the matrix algebra, what do we get? Right. So very concretely, the question is if you have a variety X, and I want to study a geometric object parameterizing Mn of K points of X, what sort of object is this and what can we say about it? Right. So let me make a definition. So the definition is that Cn of X is the object parameterizes maps from Ox to Mn. Okay. So over here I consider Mn as a non-commutative algebra, just the matrix algebra, but I'm considering this as maps from Ox, the sheaf, to Mn. For simplicity, you can just think of the case when X is affine, and maybe when like affine space, so you have n parameters, and maps like this just correspond to picking n commuting matrices inside Mn. R commuting matrices inside Mn if X is R dimensional. Right. So example, if X is AR, then Cn of AR is R commuting n by n matrices. Okay. So as another example,
but just to make sure I'm understanding, these are n by n commuting matrices of functions, right?
Of functions, yeah. So you should think of, so this is really, so in this case, this is really some scheme, which is parameterized by, so you can think of it as a sub-scheme of mn raised to r, where you impose the condition that everything commutes. So this is maybe the first example. Here's another example. If x is gm, then Cn of gm is gln. So what does it mean to say that you have a map from KTT inverse to Mn? That means that you have a matrix and an inverse of it. So that's a commuting matrix. So that's an invertible matrix. Here's maybe an example 3. If I take x equal to spec k double bracket t, so this is the completed algebra at a point, then Cn of x is the nilpotent matrices. So why is this the case? Well, there are many different ways of seeing it, but essentially if you have a power series in T, then at some point you have to start vanishing. Right? You're mapping into a finite dimensional algebra. So the image of K double bracket T is going to be some finite algebra, and therefore T is going to, some power of T is going to be 0. And because you're mapping into n by n matrices, T power n has to be 0. Okay, so these are some examples. And the case I want to make in the talk is that you should think of Cn of x as some sort of really quite good non-commutative analog of Sym n of x. And I'll try and state theorems which really try and push this analogy between these two things. Okay, so that's what I'm going for. So if you want to try and think about non-commutative cycles, whatever that means, I'm making the case that this is somehow a good candidate to consider. So this is the framing for the talk. And trying to push that framing, the first thing you might look at is if you think about Sym n of x, the very first thing you might try to do with this is compute the FQ points and try to put it into some sort of power series, and that gives you the zeta function. Right. So you can try asking what happens if I do something analogous for Cn of x. Do I get anything interesting? Okay. So let me say over here. Goal. And we'll see let's Cn of x is some sort of rough analog of Sym n of x. So here is so let me again ask it as a question. So question, what can we say? So what can we say about the n of x of FQ? Okay. So it turns out that the right thing to do. So it turns out that the right thing to do is to consider the following power series. So let me define z hat x of t be summation C n of x of FQ. I won't really need the FQ here, but let me just put it in. Divided by gn of x. So maybe I should put a GLN over here.
GLN of x means exactly.
Sorry, not GLN of x. I meant to say GLN of x. So over here I'm dividing.
Oh no, that's CNX.
That's Cn of x. That's right. So what am I doing over here? I'm taking these matrix valued point counts and I'm quotienting by the choice of a basis that I had to make when I defined Ox. So it turns out that this is actually has quite interesting properties. So maybe initially let me try and, so you can try and understand this. And maybe first let's restrict to the case where X is a smooth. So just in general, even if I don't have a smooth curve, maybe you can see that this is true. There's some sort of a product formula for this. So what is the product formula? If I take a product over X and the closed points of X, so these are not just the FQ points, but any FQ power R points, but Galois orbits of FQ power R points. What I will get is I will get this thing, which is over here, I'll get a summation of Cn of X at the local, at X. I guess I'm not quite sure how to write this, but this is the local ring at X, right? So I mean by this, the local ring at X.
In OXX or something?
Yeah, like spec OXX. And over here you want, so this is going to be the degree of X, right? And that t over degree of X. Okay, also over here it's the height of X. Okay, so what am I really saying over here? What I'm saying is that if you have some map like this, OX to Mn, you can think of this as a finite flat sheaf over X, which you decompose into its eigencomponent. So it has some finite support. So if you think of A1, right, you have one matrix, you can decompose it into its eigenspaces and it has finite support, right? So you pick off each finite eigenspace and you decompose it over the support and that gives you this product formula, right? And this object is essentially just nilpotent matrices, like OX mapping into nilpotent matrices. Because you supported local ring, it's all going to some power of discontinuity. So this sort of product formula is always true. But what happens is that in the smooth curve case, you have a much nicer product formula. So I'm going to try and explain that next. But any questions?
So where does this power series live?
So it's a formal power series, right? So these are all, so once I fix Q, this is just some number.
Okay, so this is like, what you mean by that, the number of points?
Yeah, I mean by this the number of points. So.
Okay.
So you can consider them as living in the Gothandaraman ring of varieties, for instance, if you want, but over here I'm just going to be concrete. Consider this number of points. Okay, so let me say what happens in the case when X is a smooth curve. In the case of a smooth curve, what we want to try and understand from this product formulation is what's the number of nilpotent matrices in one variable. Okay. So this is a very sort of classical fact. What's the size of the number of nilpotent matrices over FQ? Okay. So maybe some of you know the answer, but if you don't, I'll tell you a way to see it just from what we've done over here. So it turns out that this is equal to, I don't know who to attribute it to, it's a very old theorem. But let me try and say why you can see it from over here. So if I look at Z hat A1, I can write this as Z hat GM of T times Z hat K double bracket T. So what is this decomposition telling you? It's telling you that any matrix, you can decompose into some part which is nilpotent and some part which is invertible. Okay. So any matrix on a space, you can decompose into some subspace which is invertible, which is sort of the union of the, which is the intersection of the images of the matrix. Right. So this decomposition corresponds to the fact that if you have a T and an N, you can write, so let me say T is acting end of T. You can write V as a V nilpotent plus a V invertible, where this is the union of the kernels of T power I, and this is the intersection of image T. So this is sort of a canonical decomposition of a vector space into two pieces, on which T acts nilpotently, acts invertibly. So from this formulation, what you know is that this guy is going to be summation q power n squared over size of GLN q e power n. While this guy is just going to be e power n because the GLNs cancel out. And then this guy is what we want to figure out. So this is the nilpotent matrix by GLN. Right. So from here, if I just push this to the side, you'll get some expansion. And when you do the algebra, it turns out that you get this is equal to q power square n. Okay. Now it turns out that from just this computation, you can prove. So this tells you what the local factors have to be. Right? So from this computation, it turns out. Here that when x is a smooth curve, the series I just defined for you, zx of t, can be written in terms of the zeta function of x as q power minus I x e product over I mod. Okay, so this is a sort of formal product. The zeta function is some polynomial by the Weil conjectures, by the proof of the Weil conjectures. And I substitute for it instead of t, q power minus it as I goes over 1. And I just take a formal product over everything. And it turns out that this thing equals this guy. And that essentially comes from the fact that you have this sort of product decomposition locally on these guys, which is some sort of QCS identity that you can expand and verify for yourself. And one way of thinking of what I'm trying to do in the talk is to explain why you have such a product decomposition. Right? So what is the geometric reason that explains why you have this product decomposition?
Can you explain what scheme Cn of x is supposed to be?
What scheme it is supposed to be, right? So I can write down.
Talk about FQ points.
Yeah.
What are you talking about?
Right. So here's a moduli space, the definition of Cn of x. So moduli description. Cn of x represents the following functor. So Cn of x, when I plug in some t, which is t is a scheme, so t is a test scheme. This is the same as picking m over x times t, which is finite flat, along with an isomorphism. So let me define. Let me call t the projection from x times t to t. So if I push forward, so I have OT power n, the structure sheet. I pick an isomorphism as modules to the push forward of t. Right. So it's parametrizing framed finite flat sheaves over x times t, whose push forward to OT is just free as with the framing. Right. So I'm picking a basis for the push forward.
This is as OT modules?
As OT module. So
Is the isomorphism part of the data in this module?
isomorphism is part of the data. Right. So when I divide by GLN, I'm sort of removing this isomorphism. That's what this GLN is doing, forgetting the basis. Right. So for instance, if x is A1, then I'm picking a finite flat sheaf over A1 times t, whose push forward to t is just a finite basis. So this corresponds to picking, so if t was just a point, that's like picking so many points and then putting modules over each one. Right. So this is the sort of Jordan decomposition of a matrix, this picture. Okay. And if x is, okay, so another way of saying it is if I have, so more explicitly, suppose x is equal to spec z bracket, I have t1 up to t1 with some relations f1 up to fn. Right. So what does Cn of x look like? So Cn of x is then picking matrices for each of these. So it's going to be m over r. So it's going to, so the global sections of this guy are going to live inside here. Let me define it like this. So it's A1 up to AR matrices in Mn such that Fi of A1 up to AR. See. And that the AI is recombinant. Okay. So if you have a presentation for X as if you have a presentation for X as something presented over Z, then to give me Cn of X is the same as to pick our matrices for the TIs such that they satisfy all of the relations and that they all commute with each other. So this is a very explicit way of presenting what Cn of X is. Okay. Any questions about that? Okay. Yeah, so coming back to here, one way of what I'm trying to do in the talk is to explain why you should have such a product formulation. Right? So what's the geometric reason? What's the geometry?
I should have a question.
Yeah.
If you go to your take this description that you've written over here.
Yeah.
You could treat every AI as a point in affine n squared space.
Exactly. Yeah.
And then you just have like
exactly. Yeah.
And it's going to be the same scheme.
Yeah.
Okay. Thank you.
Yeah. So you that's exactly what I mean over here, that you treat the points in affine n space, affine n squared space, and you impose all of the relations that you get from expanding the matrices out from there. That's exactly it.
So of course, if you were to take n equals 1, your variety will have your scheme will have like lots of points, that's right.
If I take R equal to 1?
No, if you take n equal to 1.
N equal to 1, that's right, yeah. So if n is equal to 1, then this is just the same as this guy.
And of course, points we get for n equals 1 will induce points for bigger n by maybe taking diagonal matrices.
Yeah, for instance, yeah, that's right.
Are there is there a way to quantify points that aren't induced by points like bigger n that aren't induced by smaller n? Is there like a way to make that definition right?
Maybe put that question for a second and I'll say something which might or might not answer what you have in mind. What I will think a lot about is which are the semi-simple points and which are not the semi-simple points. Which is not quite what you're saying, but it's sort of the same thing, right? So semi-simple is when everything's on the diagonal. And that's sort of like them coming from.
Can you just justify one thing?
Yeah.
It's like, let's say, take your example 3, right? If I'm understanding correctly, what you're saying is if I take C1 of spec power series, I get spoof power series. How does it like see the topology?
So it doesn't see the topology. So just in the formal way that I've defined things, in the formal way, okay, so this thing is only for finitely presented things, right? So in general, what I'm saying is that if you use this definition, then if you have maps from K double bracket T to Mn, the image is going to be some finite algebra.
What Mn over what?
Mn over K, for instance, if you say.
Over K.
Right,
Okay.
Right. So when you take values in any T.
Oh, I see. Yes, thank you. That clarifies it. Thank you.
So this is just the variety of nilpotent matrices.
Yeah, right. That makes sense. Thank you.
Okay. Right. So what I'm going to try and explain is this guy. But you might first ask, how general is this phenomenon, right? So for instance, if I have a smooth surface, then I have some similar product formulation. So it turns out that actually things get much more complicated as you increase the dimension of X. So let me just say what happens for dimension X equal to 2. X smooth. In that case, you can prove, again, sort of by hand examining what these matrices look like, that Z hat X of T is equal to a product, this time over 2 indices, Q power minus I, T power J, where I is more than equal to 1 and J is more than equal. So you can see that this is much more complicated as a power series formulation in this guy. And for dimension x more than 2, we don't actually know of a good formulation like this. So we don't really know how to compute the point counts of x as a threefold. Right? So that's an open question. So dimension x more than 2, that's good. So to try and understand the finite field point counts of Cn of x for x more than dimension x more than 2 is just, I think we don't really have any good ideas of how to do it. So this suggests that maybe Cn of x is quite complicated in general, at least if you look at the point counts. Another invariant of Cn of x you can look at, however, is the singular cohomology or the étale cohomology. Right? And you can ask how complicated is the étale cohomology or singular cohomology of x, and maybe it also continues being complicated in general. It turns out that the singular cohomology is much more understood, and that's the main theorem of this talk. So let me state it over here. This is the main theorem. That the singular cohomology or the étale cohomology of Cn of x has this very
SymnX is a complex variety.
so either so let me say so star is either singular if x is over C or étale with QL coefficients. So either of these cases. So I don't want to, so the proof will not actually depend too much on which one I pick. So maybe you can just pretend we are in the singular world over C, if that makes you happy. But let me just state the theorem and then I'll say a bit more. So this turns out to be okay. So what am I saying? I'm saying that the matrix point counts we've been considering, the point count, or say the singular cohomology or étale cohomology, is the same as taking this Sn quotient of x power n times gln mod Tn. So Tn is the torus inside gln, where Sn acts diagonally on both factors. Okay. So, a priori, you might even wonder why we are looking at this guy. Like, what's the connection?
What's the SN action you're talking about?
So the Sn action on x power n is just
Yes, but on the other one.
right. So let me explain what the Sn action on over here is. So here's an interpretation of GLN. So interpretation of GLN mod Tn, which makes clear what the Sn action is. This parameterizes a decomposition of Kn as L1 direct sum Ln, wherein these are lines, Li. So you can think of GLN mod Tn, GLN as picking a basis, and then Tn as removing the basis up to the line. So all you remember are the decomposition as lines. So if you think of GLN mod Tn as parameterizing decompositions of Kn like this, then the Sn action is just to permute the n factors. So then Sn acts by n. Okay. So that's what I mean by section. So from this picture, you can see that there's a bundle map.
Sorry, but I'm still confused. So you're talking about permuting the columns of the matrix?
Yeah.
They could have just said that.
Yeah. Yeah. So there's a bundle map from GLN mod EN to the flag variety. But you just forget, I just remember sort of the, yeah. And the cohomology of Bn is known, and because this is a bundle map, it's a sort of a fine bundle map, the cohomology of GLN mod Tn is the same as the cohomology of Bn. Right? So the cohomology of GLN mod Tn by Borel, 10.3, shows that this is the same as, so let me stick to singular cohomology. So this is Q joined x1 to xn, where I kill the symmetric matrices. So this is the elementary symmetric matrices. All of these have the same degree. So that's what.
I really don't understand what you just showed.
So I'm saying what the cohomology of GLN mod Tn is. It's as an algebra generated by x1 to xn, and degree, all of them having the same degree, and you kill all of the elementary symmetric polynomials in the x's. So for instance, if n is equal to 2, then this is Q joined x1, x2, but you kill x1 plus x2 and x1, x2. So I'm telling you the cohomology of GL2 mod T2 is in that case, which is just P1. And over there, this condition corresponds to Q joined x1 mod x1 squared, for instance. So n equal to 2, GL2 or P2 is P1. And this is the cohomology of P1. So this is a presentation for the cohomology of P1. Does that make sense?
I still don't understand the E1 up to EN.
So the EIs of x1 to xn are a sum over all, so over indices of 1 to n, where the size of I is I. And you take the product over xj, g then. So it's an elementary symmetric polynomial. So E1 is where I look at all subsets of size 1.
So elementary,
Symmetric.
nothing to do with what, yeah, when people talk about SLN, elementary.
No. This is in the symmetric function theory, elementary symmetry. Okay. So if you're trying to parse this formula, what we are saying over here is that you have the cohomology of x power n, which is x star of x raised to tensor raised to n. You tensor with this guy, and you look at all of the things which are Sn invariants, right? So for instance, one way of constructing a class over here might be that you take a class in h star of x, and you multiply by x1, add it to multiply the same class by x2, add it to multiply the same class by xn, and then that is Sn invariant, right? So this so it turns out that this is a regular representation. So this is a regular Sn representation. With a different weighting.
What does regular mean now?
Just as
Regular representation.
regular representation.
Jesus.
Just as k bracket Sn. Right. So Sn acts in the way that. Okay. So let me maybe just quickly say what the connection between this product formula and this theorem is. So if from here I try and compute the following. So I look at the summation of the Poincare polynomial of Cn of x. So Cn of x mod JLF. Right. I look at the cohomology of this guy as a stack. I look at the Poincare polynomial. I look at p over n. So this guy is a stack. And this is the Poincare. then this, by the theorem above, tells you that you get the so it tells you that you get the same sort of product decomposition you're seeing over there, just formally from the combinatorics. Where what is this guy? So zeta b of t is the sum of the punctual polynomial of Sym of x. So what I'm explaining is sort of that this theorem as a formal consequence would give you the sort of product decomposition. Right? So if you expand out the combinatorics of what it means to write this using this formulation, it turns out that you get this product formulation. Okay. So the combinatorics are not that simple to see, but you can work it out. Although over here I'm talking about the Betti polynomial because I can't talk about point counts. So in the curve case, you still need to find a way to relate the singular cohomology or the dual cohomology to the compactly supported cohomology. But you can do that as maybe I'll explain in a bit. So it turns out that in the curve case, the singular cohomology tells you what the compactly supported cohomology is.
So this theorem of Borel, does it have like an Ital version if you know over like other fields, not over C?
I think it's true just in complete general. So this is a geometric explanation. So geometric explanation of the product formula over there. So let me, so in the rest of the talk, I want to maybe try and sketch why this is true and what this side has to do with this side, which relates to Anand's question. So that's the rest of the talk. But any questions?
Is it possible to say, is it correctly that there is a natural map from the Hilbert scheme of endpoints of X into Cn of X?
There's a natural map from the Hilbert scheme of endpoints. I think
Where
yeah.
we could achieve M, which are
Yeah,
functions of this
that's
type.
right. Yeah.
I was wondering if the idea is that it's somehow magically simpler to look at Cn than the Hilbert scheme of points?
Yes.
Or if it's possible to recover something about
No, it is much simpler to look at Cn. That's right. Yeah, and maybe I'll try and explain why. So the reason I stated this interpretation for GL and Tn is that it will help you construct a natural map from this side to here, right? And we prove that that map induces an isomorphism on the cohomology. The statement is stronger than what I've written. There's a natural map which induces an isomorphism. Let me repeat that now. So let me make a definition Sn of x as x power n mod jln Tn. What will be x? So this is the object which showed up over there. And I claim that there's a map from here to Cn of x. So what's the map? You think of this as parametrizing endpoints along with a decomposition. Right. And then what you do is you put skyscraper sheaves at each of these points corresponding to the L. So this goes to skyscraper sheaf. Li supported Li. Excellent. So this the image. So this is all the semi-simple matrices over here. Okay. So the C's are simple. Does that make sense? I can say more if it doesn't make sense, but
would you mind explaining that as an example? Like,
yeah, sure. So if x is, let's say x is a1, then and n is 2. Then what I'm picking is, so let's say x is A1. Okay. So what am I doing? I want to map from A1 squared times GL2 mod T2 into M2. 2 by 2 matrices. So if you give me 2 points, so let me say you give me λ1 and λ2. Those are my 2 points that you give me over here. And you give me a basis V1, V2. Then I send it to the matrix where T Vi is lambda I Vi.
Sorry, so I should think of the Li as the eigenspaces and the
Exactly.
size as the eigenvalue.
Exactly.
Okay.
And over here, this entire map lives over SymnX. So it turns out that there's a map from both sides down to Symn. So this is my sigma. So this map you should think of as taking the eigenvalues of your matrix. This map, you just forget the second factor. So let me call this P1, let me call this P2. Okay. So what we want to prove is that sigma induces an isomorphism from here to here. Okay. Because that's what that theorem is saying. What we'll in fact prove is that if I look at the derived push forward of P1 star of the constant sheaf, this has an isomorphism from the derived push forward of the constant sheaf over here. So if I look at the relative push forwards, then there's already an isomorphism, and therefore there's of course an isomorphism if I push forward all the way to the constant. Okay.
So like P1 is the associated bundle construction then for the regular representation.
P1 is the associated bundle construction for the, yeah. And in fact, the way we will prove this is by proving a stockwise isomorphism. So in fact, it turns out, so let me state, so in fact, the proof idea is to show that both of these maps satisfy base change formula, in the sense that if I pick a z in sim n of x, a point, then RTI star of q, the stock at z is going to be isomorphic to the cohomology of the fiber. So it's going to be isomorphic to the cohomology of Ti inverse. So that's the first step. You show that in proving this isomorphism, you can replace each stock by the cohomology of the fibers. And then you have to show that there's an isomorphism between the cohomology of the fibers. And then, so proof idea, step 1. And then step 2, show an isomorphism on cohomology fibers. Okay. So one is, so the reason one is difficult is that neither map is really proper, right? So if it was proper, then you would have proper base change theorem, which would tell you that you can compare the cohomology fiber wise. But the way we prove one is to approximate the maps by proper maps in some appropriate sense, right? So maybe I won't do that for lack of time, but maybe I'll focus on 2 because that has more interesting geometry. And sorry, I should have stated this before. This entire theorem over here has some conditions, and I'll say the condition right now. But we expect that the condition can be true. Let me say what I mean. So the condition we need. So condition in care not equal to 0 that we need is that every local ring of X has a gradient. Okay, so this is sort of a strange condition. For instance, if X was smooth, this would always be true, right? And you can think of this as saying that every local ring has a GM action, which is really what we need. Right? And the reason we need it will become clear in just a second, but we expect that the theorem is true in complete generality. This is sort of an artifact of a proof. Okay, so let me say how we prove 2. So proof of 2. So 2 is this guy. You want to show an isomorphism of the fibers. So what are the fibers of this map? So what are the fibers of the map? Right. So if I have a Z on Symn of X, I can think of it as a 0 cycle. So let me write it as lambda I xi, where lambda is the multiplicity of xi. So let me think of it this way. Then what turns out to happen, and you can, okay. So what's the fiber? So what is P1 inverse of Z? So what are we requiring? We're requiring that I have fixed my points in the base, and over here I want to pick these lines, but up to the Sn action. So this guy is the same as GLN mod En, but modulo S lambda. S lambda is the product of S lambda. So the way to see this maybe is that if instead of mapping down to Symn I map down to X power n first, then the fiber is just going to be GLN mod Tn. And then I want to quotient out by the Sn action, but the Sn action will have a big orbit, and the stabilizer of any point in the orbit will be exactly S lambda. Okay. So let me write this out. So you have this map from Sn of X down to X power n, and then down to Symn of X. So if I pick my point Z, that will have some fiber. So let me put this pi or theta. So theta inverse of Z is going to be a bunch of points. And then in figuring out what the fiber over here is, I need to pick a stabilizer of a point in theta inverse of Z. And the stabilizer of a point here is S lambda. So that's where this S lambda comes from. Okay. Then let me talk about the 2 inverse of Z. This is a little bit more complicated, not too much. What will happen over here is that, okay, you're looking at this map from Cn of X to Symn of X. So if I have my points, which are supposed to be the eigenvalues, the points xi, at each local point, I have to give you a matrix which has size lambda I. Right? So I have to give you a matrix which is nil lambda I of the local ring at xi. But this guy comes with a basis on that space. But what I want is a global basis, a global frame. So I want to pick a global framing. But then I have to quotient out by the product of GL lambda. So this quotient acts diagonally on both of the factors. And this one is removing the basis I picked over here. And I express the basis for GL in terms of the basis I picked over here. So that's what I get. And what I want to prove is that sigma, which induces a map from here to here, so sigma induces a map from here to here, I want to prove that this is an isomorphism on cohomology. Right? Okay. So why do I need this condition? When I have this condition, it turns out that all of these are contractible. So why is that the case? Suppose I have a GM action on this guy.
So do you want any GM action or like one that lifts on the tangent space just or something? Do you want to recover? Do you want to like split the filtration by the part of this idea or?
I want, yes, exactly. Okay. Yeah. So when I say has a grading, the grading is compatible with the maximum. Yeah. So if I have a GM action, then I can use that to push everything down to 0. Right. So if I had a GM action, that would tell me that this is contractible. In characteristic 0, you can get away by doing something else because you have a unique closed orbit. And it turns out that everything contracts with the unique closed orbit. So in characteristic 0, you don't need this condition. And this is homotopy in characteristic 0. But in characteristic P, when I have a GM action, I can say that this is contractible. So this is contractible under condition. Okay. So then, because this is contractible, I can ignore it for the purpose of computing the cohomology. And then I want to understand the map from here to here. But that turns out to be a affine bundle map. So that's a bundle. And what are the fibers? The fibers, so the fibers of GLN mod En mod S lambda to GLN mod product of GL lambda I are GL lambda I modulo the torus here modulo S lambda I product over. Okay. So what are we saying over here? We have this decomposition into subspaces, not of the ordering. And then I want to map it down where I forget the individual subspaces within the subspace, within each lambda, right? So if I'm given a point over here, if I'm given a decomposition into subspaces of dimension lambda I each, then to recover this thing, I have to pick for each one, I have to pick a decomposition into lines, but up to the permutation. And then the cohomology of this guy, we already found over here. It's the SN invariance of this guy, which is just trivial because it's a regular SN representation. Right? So the cohomology of the fiber is trivial, which means that the spectral sequence degenerates, which proves that the cohomology are equal. So really the proof that the cohomologies are equal goes through multiple reductions. I didn't really explain this one. But for the second one, what happens is that a bunch of things that turn up that you might be afraid of turn out to be either contractible or have trivial cohomology. And so the cohomology matches. Right? So it turns out that really the cohomology is much easier in general. And it's because you have access to Sn of x that this Cn is much easier to study than Hilbert n in some sense. Right? So it turns out somehow that the semi-simple locus really controls all of the cohomology of everywhere matrices, which is maybe not what you would expect initially. Okay. So in the last 5 minutes, I could try and tell you why in the curve case, this tells you something about the compactly supported cohomology. And the reason is simply because there's a nice bundle map. So in the curve case, you can consider Cn hat of x. What is this guy? This is Cn of x plus flag on Kn compatible with okay. So Cn hat of x you should think of as somehow killing the Sn equivariants that you have. Right? So you're picking an ordering on the eigenspaces. You can think of it that way. So what I'm doing is taking a matrix valued point of Ox and then picking a flag on the target, which is compatible with the Ox action. This maps down to x power n. Right? And what's the fibers? Well, if I pick the eigenvalues, then I'm just left to tell you what all the other matrix values are. So this is a bundle map. So this is a bundle with fiber upper triangular matrices. And because this is a bundle with affine fibers, that tells you that that this has a very nice structure, so that the compactly supported cohomology is basically the dual of the singular cohomology with some twisting. Right. So that tells you that the compactly supported cohomology also has a similar structure. So Xn is smooth, and you have a affine bundle over something smooth. That tells you what the compactly supported cohomology is. So this explains Y dimension 1. So this plus the before singular cohomology computation explained Y. Okay, so maybe I'll stop over there.
Questions?
I mean, maybe this is naive, but what stops you from trying to do this for other split reductive groups?
Nothing, and we are trying, and we have some results.
Well, is it easy to point out? Because I mean, almost step by step by step, there's an obvious guess of what should be replaced, but is there like an obvious roadblock?
Not that we can see.
Okay.
I think things should work out in general.
Okay.
Just depending on the details takes a bit of time.
Thank you.
In the paper that we have, we do treat with the Hermitian case in the real sense, and that also has a nice decomposition. That's completely immediate. In general, what happened was that we had a completely different proof before, which was hard to generalize. And then almost at the last minute, we found this very sort of elegant proof. So then we had to go back and work things out. But so there was, well, one of these authors is on the job market this time. So we didn't want to push too much the paper before getting it out. So that's part of the issue why.
So can I ask just a small follow-up? So like the funny thing is that once you put it in this context, you see that like the SN and SymnX, you should sort of think about as the Weil group for GLN.
Exactly.
Have people considered for other Weil groups analogs of SymnX independently of sort of this picture?
That's a good question. I don't actually know. I don't know. I think that would be interesting to study. Yeah.
Can I ask an even more naive question? So,
of course.
it's very nice, but I feel like this is sort of a pitch for like either understanding the Hilbert scheme, as was said, or replacing it with something.
Yes.
Can you just, for someone who knows nothing, give some like ideas for applications or how are you thinking of this?
How am I thinking of this? Well, I guess the idea I had was very nice. A long time ago, I was trying to think about what the simplest non-commutative geometry might look like. And the naive idea is that maybe just replace points valued in fields with points valued in matrix algebras like this. So then you start trying to think about the space, and then you find out that there are all of these nice things. So my pitch is really, I guess, that this is somehow a good replacement for Sym n of x, and from a different perspective for Hilbert, because you can prove more things about this. And really, we were very surprised that you can compute the cohomology of Cn of x and complete generality like this. Because initially we could do it for the curve case, maybe try to do something for the surface case. The compactly supported seems very hard. Hilbert, of course, is very hard to study. The cohomology of in general, the sorts of structures. Really, Cn of x has much more structure, right? Like there's the sort of correspondence you can build between things. So there's a lot more structure to. So really, this bundling up of things together in terms of this zeta function that I had before, that suggests that somehow you should really consider all the Cn together, and there's some nice algebra structure on that, similar to what happens for Hilbert with the Nakajima algebras. So there's really, I guess what I'm pointing at is that there's this really interesting object which seems to have a lot of structure, which is sort of close to what other people have considered, like Hilbert, or the quotient of this by GLN is coherent schemes on N, which is a stack which people have studied. So the things close by which have been studied, but Cn of x itself doesn't seem to have been studied that much. So maybe that's the pitch.
So imagine you have an affine variety in some affine space with coordinates x1 up to xn.
Yeah.
And fix an ordering of these coordinates so that when you write an equation, you have x1 to a power x to a power. Okay. Now you could, once you fix these orderings, you could ask for matrices, so to speak, A1 up to AN, which don't commute anymore. But you can just plug them in and in the order that you specify.
Yeah.
And
and you can
so
ask
for example, I mean, so the kind of idiotic case of this would be like just if your equation is f of x equals g of y, and x and y are just two matrices of the same size, and it's a meaningful question.
Exactly.
So it seems like in some, I mean, kind of more natural in a way. I mean, forcing your n matrices or however many matrices to commute with each other, it's some kind of weird constraint.
I completely agree. Actually, I think the more natural thing would be to not impose this commutativity and study something more general. I haven't tried too hard. But one thing I do know about is you can study mild non-commutativity. So you can have two variables xy, where xy is q times yx, for instance, where q is some parameter. And then over there, you can ask what are the point counts, or xy is some other parameter, like a root of unity times yx. And you can ask what are the point counts of this matrices which have this property. And over there, you do get some nice product formulas like what I've been describing over here. So there really does seem to be more geometry, not just in the commutative case, but more generally. So I think that's a great question. I think there is something to be said over there. That's what I would say.
Other questions? Thank you very much.